Okay, yeah, so let's start. I'll share my screen. Oh, wait, I can't share my screen. Okay, yeah, now I do. Is my screen visible?
Yes.
Yeah. Okay, so let's start. So first, let's recall what we saw in this week. We saw that last week we had seen that the decision version of bipartite perfect matching was in RNC, and this week we saw that the search version is also in RNC. Now, RNC is a class of sort of decision problems, so it doesn't exactly make sense to say that a search version of some problem is in RNC. So here we are slightly abusing the terminology, and what we mean is actually that the search version of bipartite perfect matching also has sort of randomized circuits uh, of type like randomized circuits that look like NC circuits, but they can have multiple outputs. Yeah, so there is a slight abuse of terminology over here. Then the next thing that we saw was the isolation lemma, and this lemma was basically used to show that the search version of bipartite perfect matching is in RNC. The lemma is as follows: let script f be a family of subsets of E. E is some set. Suppose that to all elements E in E, we assign a weight W of E uniformly at random from a set S subset of R. And for any F in the family, we define the weight of F as WF is equal to sum of weights of all the elements in F. Then the lemma says that the probability that with probability at least 1 minus size of E over size of S, there is a unique F in script F with minimum weight. So in case of bipartite perfect matching, our family F would be the family of perfect matchings, and E would be the set of edges. Then we also saw the semantic and syntactic and semantic complexity classes. So last time you were asking me about this, right?
Yes.
Yeah, so is it clear or should we discuss this?
Yeah. I mean, if you can repeat.
Okay, yeah. Okay, so in class we didn't exactly see the formal definitions of these two classes, but what we saw was the following. For a class C, we say that a machine M is a C verifier or a C decider if there exists a unique language L. Okay, let me write, that would be easier. Okay, so I have, yeah, for a class, complexity class, C, we say that a Turing machine M is a C decider if there exists a unique language which will denote by L of M, which M accepts, but according to the acceptance criteria. Of the class C. So generally when we say that a Turing machine M accepts a language, what we mean is that at least one computational path leads to accept, then and only then we would accept it, right? But over here, LM is the language accepted by M according to the acceptance criteria of the class C. So for example, if C were NP, then the criteria would be that there exists an accepting path, but if the class were BPP, then the accepting criteria would be that X is in LM if and only if the at least 2/3 many fraction of paths accept, and x is not in the language, then at least 1/3 of the paths not accept. Okay, so that's how we define this language LM. And so we say that a Turing machine M is a seed decider if such a language LM exists. Now consider the problem of deciding, okay, whether a given Turing machine is a C decider. For syntactic classes, this problem is easy. And for semantic classes, this problem is undecidable. Okay, so now N is the class NP is a syntactic class. Why? Because so the problem for this, where is this? Yeah. So this problem for NP would be to decide whether a Turing machine is an NP decider or not, and every Turing machine is an NP decider. Why? Because like given a Turing machine, the language LM would just be the language of all strings X, such that there exists at least one accepting path, right? So for every Turing machine M, you can create a unique language LM, and so every Turing machine is a C decider, is an NP decider. So the problem of deciding whether a given Turing machine is a C decider or not is very trivial. Yes, it is. Every Turing machine is. But for BPP, the problem of deciding whether a given Turing machine is a BPP decider is problematic, because if I give you a Turing machine, how could you ensure that there does not exist a string which the machine accepts with probability, let's say 0.5? So in fact, you can show that the problem of deciding whether a machine is a BPP decider or not is undecidable. So BPP is a semantic class. Is this fine?
Yeah, so this easy problem, this easy is on a deterministic Turing machine?
Okay, easy, okay, so easy as in this case, by easy I mean decidable.
Okay.
But yeah, okay, so what would end up happening is easy would be decidable and decidable would be trivial. So either the answer would be yes for every Turing machine or no for every Turing machine. So yeah, easy would be like NP. So easy would actually end up becoming trivial.
Yes.
Yeah. That's why I sort of use this loose term easy. Yeah. So then you saw the definition of promise problem, which are sort of a generalization of a language. So a promise problem is a tuple pi of pi yes and pi no, such that pi yes and pi no are both sets of strings and their intersection is empty. Strings in pi yes are called the yes instances of the promise problem pi, and strings in pi no are called no instances of the promise problem pi. And we say that a Turing, yeah.
Yeah, so how this promise problem is a generalization, because in the language we have any arbitrary string of the language we can decide upon, but here we have instances, yes instance and no instance, and for some problems don't care.
Okay.
So in what sense it is a generalization?
Okay, so take a language L. I can write it as a promise problem as follows. L yes is a set of all strings which are in the language. L no is a set of all strings which are not in the language, right? and then both keys are
Yes.
satisfied, right? So a language is a promise problem,
Yes.
but a promise problem is not a language, right? Because there can be something which is neither a yes instance nor a no instance.
Oh,
So
oh,
something that is not in the language, but also not in the language.
okay.
Right. Yeah. So sort of in this way. So basically, promise problems can handle this third case as well. This sort of gray area as well.
Yeah.
Yeah.
Yes.
Yeah. And we say that a Turing machine M decides the promise problem pi if for all x in pi yes, that is for all yes instances, mx equals to 1, and for all x in pi no, that is for all no instances, mx equals to 0, and for instances which are neither yes instances nor no instances, mx can be either 0 or 1. So you don't care what mx is. Another way to look at this is the following: when you give m an input, you are making it a promise. It's either a yes instance or a no instance. In that case, m would output 0 or 1. But if you remove this promise, then m is helpless. It would do anything, output 0 or 1. So that's why we call these problems like promise problems. So then you saw one concrete problem called USAT, and the yes instances of this problem are all Boolean formulas with a unique satisfying assignment, and no instances of this problem are all Boolean formulas with no satisfying assignments. Now there can easily exist Boolean formulas which have satisfying assignments but have more than one satisfying assignments. In that case, they would neither be yes instances nor be no instances, and so this is like sort of a strict promise problem, like this is not a language. And then you saw the Valiant-Vazirani theorem, which says that if USAT is in promise P, then NP equals to RP. So promise P is basically the analog of P, but for promise problems. So a promise problem is in promise P if it can be decided by a deterministic Turing machine. A polynomial time deterministic Turing machine. And then you moved on to counting complexity, and the first thing that we saw over there was the definition of the class Fp. This is just the function analog of class P. So this is the class of all functions f from 0, 1 star to 0, 1 star computed by polynomial time deterministic Turing machines, and sharp P is a class of all functions f from 0, 1 star to 0, 1 star such that there exists a polynomial time non-deterministic Turing machine n, so that for all x in 0, 1 star, f of x is exactly equal to the number of accepting paths in the computation graph of n on input x. And then we also saw the notion of sharp P completeness, and this a function f in sharp P is said to be sharp P complete if for all functions g in sharp P, g is in fp to the p, that is g reduces to f in polynomial time, but not using Karp reductions, using Cook or Turing reductions. So is this fine? Then if it is, then we can move on to the problems.
Yes.
Right, yeah. So the first problem is the following. So in the last slide we saw a definition of the class sharp P using non-deterministic Turing machines. Now the problem is, give an alternative and equivalent definition of sharp P but using deterministic Turing machines. So would you like to guess what this definition is?
Because if we convert NDTM to DTM, it will be upper bounded by 2 to the power polynomial in n.
Right.
So I think it will take exponential time on a deterministic Turing machine to count all the possibilities.
Okay, right. So the class that you are suggesting would be like, okay, not would be, but can be a superset of sharp P, right? Because like if you allow exponential time, you might be able to do some more than NP, right? So more than non-deterministic, more than what you can do in non-deterministic polynomial time, right? Because right now we don't know if exp equals NP, right?
Yeah.
Yeah. So that what you are suggesting would be a superset of sharp P. But again, yeah, so you are right. There we just have to exploit some connection between non-deterministic Turing machines and deterministic Turing machines. And there is one connection which is the following. Given a non-deterministic Turing machine, you can think of it as a deterministic Turing machine with certificates, right? So instead of taking just
Yes.
one input, it would take two inputs, string X and a certificate, right?
Yes.
And this is exactly what we'll do over here, and this is exactly what we did to define NP using deterministic Turing machines, right? So the definition is the following. Sharp P is a class of all functions f from 0, 1 star to 0, 1 star such that there exists a polynomial time deterministic Turing machine M and a polynomial function p from n to n satisfying the following. For all x in 0, 1 star, f of x is equal to the cardinality of this set. The set is y in 0, 1 to the p of size of x such that mx, y equals 1. That is, it is exactly equal to the number of certificates which make m except x, right? And because of this sort of equivalence between Turing machine with deterministic Turing machine with certificates and non-deterministic Turing machines, you can actually show that these two definitions are equivalent. So I won't do that over here, but you can try it on your own, and if you still have some problem, you can either ask the question in the forum or we can discuss this next time. Okay.
Yeah.
Yeah.
Yes.
And sometimes this definition comes in handy. It sort of makes things a little clearer because deterministic Turing machines are sort of sometimes easier to reason with than non-deterministic Turing machines. Now let's move on to the second problem. So this is a problem about isolation lemma. So suppose script f is a family of subsets of E equals E1 to E100. Suppose we assign weights W uniformly at random to the elements of E from the set 1 to 1000. The weight of a set F in script f is defined to be the sum of the weights of elements in F. Compute a lower bound on the probability that there exists a unique minimum weight set in the family F. So what's the answer to this one?
1 minus cardinality of E by cardinality of S.
Right.
So 1 minus 100 by 1000.
Right. So in this
So,
case,
9 by
yeah,
10.
that is 0.9.
Yeah.
Yeah, the
Yes.
same thing, right?
Yes.
Yeah.
Yes.
Yeah, so the answer is exactly what you said, but let me just write it down. So from the isolation lemma, probability that there exists a unique minimum weight set in script f is upper bound, sorry, is at least is at least 1 minus size of E over size of S, which in this case is 1 minus 10 over 1000, sorry, 100 over 1000, which is 1 minus 0.1, so 0.9. So the next few problems are just recall problems. So from the below choices, choose the most accurate statement about the Mulmule-Vazirani algorithm for outputting a perfect matching in parallel. The options are: it always outputs a perfect matching, it does not necessarily always output a perfect matching, even if there is a unique minimum weight perfect matching. If there is a unique minimum weight perfect matching, it outputs a perfect matching, and if there are multiple minimum weight perfect matchings, it outputs a perfect matching. So what's the most accurate way of it summarizing what MVV algorithm does?
I think C.
Right, yes. Yeah, so it's C. The reason is the following. So the MVV algorithm assigns a random weight to each edge. And then using the isolation lemma, it argues that there is a unique minimum weight perfect matching. But just as we saw in the previous problem, the isolation lemma can fail with a non-zero probability, right? So for example, in the previous question, it failed with probability 0.1. So there is a non-zero probability that there won't be a unique minimum weight perfect matching. In this case, the algorithm may or may not return a perfect matching. We can't say anything because it's randomized, right? However, if there is a unique minimum weight perfect matching, then recall that the algorithm finds a perfect matching. In fact, it finds that unique minimum weight perfect matching and outputs it. So the closest option is C. If there is a unique minimum weight perfect matching, it outputs a perfect matching. So let's move on to the next problem. The next problem is the MVP algorithm shows that the problem of outputting a perfect matching for a given bipartite graph is in which of the following complexity classes: RP, NC, AC, RNC, or P/poly. So what's the answer to this one?
RNC.
Right. Yeah, this is just a recall problem. We saw this in the recap section as well. So the next problem is, out of the following choices, select all that is or are semantic classes, and there may be multiple correct answers. The options are PP, BPP, CoRP, and P. So what are the correct options?
BPP is there, but I mean, I don't know other than BPP.
Okay, so BPP is certainly there. What about P? So when is a Turing machine a P decider? Basically, a Turing machine is a P decider if it's a deterministic Turing machine, right?
Yeah.
So if I give you a Turing machine, if I give you the encoding of a Turing machine, it is very easy to find out whether it is deterministic or not, right? Just parse the encoding and see if it has just one transition function, right?
Unique configuration.
Right.
Yes.
Yeah, so from the very encoding of the Turing machine, you can tell whether it has one or more transition functions, right?
Yes.
Right.
Yes.
So P would be a syntactic class. What about CoRP? So recall that a machine would be a CoRP decider if let me write it. CoRP decider. So M is a CoRP decider. If and only if for all x in 0,1 star either probability that mx is equal to 1 is 0 or so either it always, so if x is not in L, so if x is in L then okay, no wait, if x is not in L then it should always say that, yeah, that's right, sorry, yeah, greater than, let's see if this is correct. So if x is in the language, then it should accept with probability at least half, and if x, oh wait, so no, I wrote for RP. So if x is not in the language, then it should accept with probability at most half. So at most half, and if x is not in the language, wait, so if x is not in the language, then it should accept with probability at most half, and when x is in the language, it accepts. Okay, so now how do you guarantee that this is always satisfied? So how do you guarantee that for every string it's either this or this? So this is like sort of the same problem that we face with BPP decider, right?
Yes.
Right. So decide so uh, deciding whether a given Turing machine is a co-RP decider or not is also like an undecidable problem. So BPP and co-RP are certainly semantic classes. Let's look at PP. So M is a PP decider. And only if for all x in 0, 1 star, probability mx is equal to 1. This is either greater than half, or probability mx is equal to 1 is less than or equal to half. Now, unlike in the case of BPP and co-RP, there is no gap over here. There is no gap over here between these two numbers, right? So,
Yes.
no matter which Turing machine you pick, and no matter which string you pick, either at least half of the parts would either at most half of the parts would accept, or either at least more than half of the parts would accept, right? It's either this or this. There is nothing in between.
Yes.
So every Turing machine is a PP decider. So again, deciding whether a Turing machine is a PP decider or not is trivial, right?
Yeah.
So PP is also a syntactic class. So the answers are BPP and co-RP. Yeah, so problem 6. Let phi be the Boolean formula. Phi is equal to x1 or x2 complement or x3 and x1 or x2 or x4 complement. Suppose M is a machine that is a decider for the promise problem of USAT. If phi is given as input to M, which of the following is the expected answer? Choose the most appropriate option. M would always accept, M would always reject, M can either accept or reject, both are acceptable, and it should report that it is an illegal input. So would you like, so this sort of needs to be worked out, but would you like to take a guess?
I mean, if phi has a unique uh, I mean, I'll have
Right.
to see if it is uniquely satisfied or not.
Right, so that is exactly what this question boils down to, deciding whether phi has a unique satisfying assignment or not. Yeah, so let me tell you the answer. The answer is it can either accept or reject, both are acceptable. Oh, and the reason is the following. So let's consider this assignment. x1 is equal to 1, x2 is equal to 0, x3 is equal to 0. So this is a satisfying assignment, right?
Yes.
Okay, so this is definitely not a no instance. Okay, and let's look at this assignment. x1 is equal to 0, x2 is equal to 1, x3 is equal to 1. This is also a satisfying assignment because x equals to 1 means this is satisfied, x2 equals to 1 means this is satisfied, so both are satisfied, both are true. Also a satisfying assignment, right? So phi is also not in USAT yes. And since phi is neither in USAT no nor in USAT yes, M can do anything, right?
Yes.
Right. So the option is C. It can accept or reject, both are fine.
Yeah.
Yeah. So the next problem is, which of the following options captures the message of the Valiant-Vazirani theorem most accurately? USAT is easy. USAT is not easy but easier than SAT. USAT is likely to be roughly as hard as SAT, and USAT is much harder than SAT. So this asks you to sort of interpret the Valiant-Vazirani theorem in some way, and so which of the four options is the closest interpretation?
I think USAT is as hard as SAT.
Right, yes, yeah, that's the correct answer. So let's see why. So how do we prove the Valiant-Vazirani theorem? So to prove the Valiant-Vazirani theorem, we show that SAT reduces to USAT under randomized polynomial time reductions, right?
Yes.
So if we have an efficient algorithm for USAT, we would also have an efficient algorithm for SAT. The caveat would be that this algorithm would be randomized. So
Yeah.
so the theorem says that USAT is likely to be roughly as hard as 3SAT. That should be roughly over here. Roughly because, okay, generally when we say something is as hard as some A is as hard as B, we mean that like if you have a polynomial time algorithm for A, you also have a polynomial time algorithm for B. But in this case, a polynomial time algorithm for USAT translates to a randomized polynomial time algorithm for SAT. But that is fine enough because randomized polynomial time is also a reasonable definition of efficient, right? So
Yeah.
the theorem says that USAT is likely to be roughly as hard as SAT. Likely to be roughly. Yeah, so now let's move on to the next problem. So next problem deals with pairwise independent hash functions. So let us consider the following family script h of pairwise independent hash functions from 0, 1 to the n to 0, 1 to the m. H is the set of all functions h of ab defined as ax plus b mod 2. So all the operations, multiplication, addition, everything is happening mod 2, such that A is any matrix in 0, 1 to the m cross n. So it's an m cross n matrix whose entries are 0 or 1, and B is a vector in 0, 1 to the m. So it's a vector whose entries are it's an m dimensional vector whose entries are 0 or 1. Now suppose we choose h uniformly at random from this family script h. Given three distinct vectors x, y and z in 0, 1 to the n, and three vectors r, s and t in 0, 1 to the m, what can we say about the three events? Hx equals to r, hy equals to s, and hz equals to t. The options are all three events are independent. Option B is any of the two of the three events are independent, but all three events need not be independent. Any two of the three events are also not independent, and the three events are mutually exclusive. So what's the correct answer?
I don't have any idea.
Okay. Yeah, so the correct answer is B. Any of the two of the three events are independent, but all three need not be independent. And this almost directly follows from the definition of this almost directly follows from two facts. Number one, definition of a family of pairwise independent hash functions, and number two, the fact that we proved in class that script h is a family of pairwise independent hash functions. Okay, so let me state this. In class we saw that pairwise NDP dependent hash functions. And we also know that the definition of the pairwise independent definition of a family of pairwise independent hash function is as follows. So H is a family independent hash functions if and only if number 1 probability where H picked at random, H picked uniformly at random script H oh no wait, I forgot a quantifier. For all x in 0, 1 to the n, probability H picked uniformly at random from script H of x is equal to R. This is exactly equals to 1 over 2 to the m, so 1 over the size of the domain, and for all R in 0, 1 to the m, I've got this as well. So for any x in 0, 1 to the m and any r in 0, 1 to the m, probability that if you pick a random function from this family, h of x equals to r is exactly 1 over 2 to the m. That is, this random function distributes x uniformly over the domain. And the second property is this: for all x, y in 0, 1 to the n, x not equals to y, and all r, s in 0, 1 to the m, probability over h picked uniformly at random from script h of x equals to r and h of y equals to s. This is exactly equals to probability h picked uniformly at random from script h of x equals to r times probability h picked uniformly at random from script h of y equals to s. So what does the second statement say? The second statement says that if x and y are distinct, then these two events hx equals to r and hy equals to s are independent, right?
Yeah. Yes.
So
how do we read this epsilon under R?
oh, so sorry, this is not epsilon under r. Let me write it more clearly. This is belongs. Okay, so when we say that h, this symbol script h, what we are saying is the following: h is picked uniformly at random from script h. So like for example, if I wanted to read this, I would read this as probability over h picked uniformly at random from script h of hx equals to r and hy equals to s is something.
Oh.
Yeah. So this belongs here. So next problem also deals with pairwise independent hash functions. Yeah. So consider the family H of pairwise independent hash functions from the previous problem. Suppose H is chosen uniformly at random from script H, given x in 0, 1 to the n, and a set S subset of 0, 1 to the m of size 2 to the m minus 2. What is the probability that hx is in S? So would you like to guess what the answer to this is?
Hx is in S.
So
So
H has
2
these
to
two
2.
properties.
Uh, I'm not sure, but 2 to power m minus 2 into 1 by 2 to the power n.
That's exactly the answer. Yeah. So it's 1 over 4. Well, and 1 over 4 would exactly be that, right? 2 to the m minus 2 over 2 to the m, right?
E.
Yeah. So let's see why. So yeah, we have this, right? No, rather not, let me not write this property because I've already written it over here. So I was just going to rewrite this property, but I've already written it over here, so let me not rewrite this. Let me just calculate. Okay, so for any x in 0 comma 1 to the n, probability when h is picked uniformly at random from script h, h of x is in S. So this probability is the same as this probability, right? H picked uniformly at random. Union over R in S. Union R capital S, H of X is equal to R. So these two events are exactly the same, right?
Yes.
Now what do we know? From union bound we know this. This probability is upper bounded by R in S probability H picked uniformly at random from H of X equals to R. And this we already know the value. We already know the value of this, right? It's 1 over 2 to the n. But if we put this value over here, that would just give us an upper bound on the probability, right? We want an
Yep.
equality. Okay. So this is because of union bound. But what I'm claiming is the following. In this case, you don't even need something as sophisticated, or not as sophisticated as union bound, but something as much something. So in this case, you don't even need union bound. You can do something much more simpler. Observe the following. If for R1 not equals to R2, okay, let me write that over here. For R1 not equals to R2, Hx equals to R1 and Hx equals to R2 are exclusive, right? So when R1 and R2 are different, Hx equals to R1 and Hx equals to R2 cannot happen together, right? Because H is a function. Now what do we know? We know that the probability of union of a bunch of mutually exclusive events is exactly equal to the probability of the sum of those events, right? Sorry, sum of the probability of those events, right?
Yeah.
For mutually exclusive events, this actually becomes an equality. And in this case, our events are mutually exclusive. So this is an equality. So this is sum over R in S 1 over 2 to the m, which is equal to size of s over 2 to the m, which is 2 to the m minus 2 over is equal to 1 over 4. Okay.
Yeah.
Yeah. So the next problem is also somewhat similar. So consider the family script h of pairwise independent hash functions from problem 8. Suppose h is chosen uniformly at random from script h, given 2 x comma y in 0 comma 1 to the n, and a set S subset of 0 comma 1 to the m of size 2 to the m minus 2, what is the probability that hx and hy both are in S? So would you like to take a guess what the answer is? Okay, so yeah, I mean this definitely needs to be worked out. But yeah, so let me tell you the answers are, there are two cases. If x equals to y, then the answer is 1 over 4. And if x is not equals to y, then the answer is 1 over 16. So let's see why this is, let's see why these are the answers in both of these cases. Okay. So is the question clear?
Yes.
Right, yeah. So let's see both of these cases. Case 1. In that case, probability that, okay, so there is always this h picked uniformly at, so this is always there. But from now on, to simplify the notations, I won't use this, okay, but this is always present. I just won't write this. So probability h of x and h of y both, or rather let me write it like this because that's what we'll do later. Probability h of s is in x and h of y is in s is exactly this probability. H of x is in s, right? But we saw in so this solves the first case, right? When x equals to y.
Yes.
Right, so this is the first case. Now let's do the second case. This is slightly lengthier. So case 2. X is not equals to y. Then because script h is a family of pairwise independent hash functions, we have this, right? So I'm just rewriting that property. This is exactly equals to probability hx equals to r times probability hy hy is equal to s, and both of these probabilities individually are 1 over 2 to the m, right?
Yes.
Okay, no, let me just keep it in this form because this is what we'll use. So this is just from the definition of pairwise independent hash function. So far we haven't done anything for this problem. Okay. So first question, why couldn't we use this in the first case?
This means I mean, which part we couldn't use in the first case?
So why couldn't we solve the first case as well using this statement, this entire statement?
Because x was same as y.
Right. So yeah, so what I want to clarify over here is the following. If H is a family of pairwise independent hash functions, you have this independence guarantee only when x is not equals to y. Okay.
Yeah.
Yeah, otherwise you don't have this independence guarantee. Otherwise, in fact, the events would trivially not be independent.
Yeah.
Because they would be the same event. Okay, either same event or completely different events depending on whether R and S are the same or not. Yeah. So we have this. Now what do we want in this problem? In this problem, rather in this case, we have this. Hx in S and Hy in S. So this is the same as this, right? Small s and capital S. H of x is equal to R and H of y equals to S. So these two events are the same, right? These two events inside the brackets. So now over here, no. So okay, my claim is this. The probability in the previous problem is, the previous step is this. Sum over R in, I should write capital S properly. Small s in capital S, probability Hx equals to R and Hy equals to S. So my claim is that this probability is exactly the same as this probability, and the reason is the following. Because for R1 comma S1 not equals to R2 comma S2, the events Hx equals to R2 and Hy equals to S2 are mutually exclusive. Is this fine?
Yeah.
So we are taking union over these like pairs, and
Yes.
if the pairs are different, then the events would be mutually exclusive. And so if you so if you expand this expression out, you would get things like h of x equals R1 and h of x equals S1, h of x equals R1 and h of x equals S2, and so on, right? So for
Yeah.
every pair R and S, you would have one such event. All of those would be mutually exclusive. So you can just do what we did in the previous problem and sum them up. Now this becomes easier. So continuing from here, this is just sum over R in S, sum over S in S of 1 over 2 to the m times 2 to the n. This we just saw over here, right? And this is just equals to 2 to the m minus 2 times 2 to the m minus 2 over 2 to the m times 2 to the n. So this sum gives me 1 to the m minus 2 because this is exactly size of s many times. This is also again size of s many times, so I get this. This is just, this is 1 over 4, this is 1 over 4, so is this fine?
Yeah.
Yeah. So now let's move on to the next problem. Yeah, so I think this is the last problem for today. So out of the given Boolean formulas, which one is a yes instance of the promise problem USAT? And this statement over here is crucial. All of the below formulas are to be considered as formulas over the two Boolean variables x1 and x2. Select all the options that are correct. The options are x1 and x2, x1 or x2, x1 complement and x1 or x2 and x1 complement or x2 and x1 or x2 complement. So would you like to guess which of these are yes instances of the promise problem USAT?
Certainly A is there, x1 and x2, and I think D.
Okay, what about C?
C actually 0, so it will become 1, and we can assign 1 then. I mean,
Okay, yeah, so you are right. The answer is just A and D. Why the answer is not C? Even though there is just one satisfying assignment of x1, x1 equals to 0 for this, which this is 1. I'll tell you when we actually solve the problem. Okay.
yeah.
So my question was this. Okay, look at the formula x1 complement. There is just one satisfying assignment x1 equals to 0, right?
Yes.
So this will also be yes instead of USAT, but it is not. That we'll see when we solve the problem. Yeah, so the answers are A and B, and the reason is the following. So yeah, let's see option A. So for option A, it's x1, x2, and it was x1 and x2, right? So if x1, x2 is 0, 0, then 0 and 0 is 0. If x1, x2 is 0, 1, then 0 and 1 is still 0. If it's 1, 0, then 1 and 0 is still 0. And if x1, x2 are both 1, then x1 and 1 is 1, right? So this is a yes instance. Now let's look at B. B is x1, x2, and it's x1 or x2, right? So if x1 and x2 are both 0, then 0 or 0 is 0. If at least one of them is 1, then the OR function is 1, right? So this is not a yes instance. Nor a no instance. So now let's look at the third option, C. C is, so the crucial statement was this.
So we have to consider both x1.
Right.
It should be a formula both x1,
Yes,
x2.
exactly. That was a crucial statement. X1 complement. So if x both are 0, then x1 is also 0, so x1 complement would be 1. If x1 is 0, x2 is 1, x1 complement would still be 1. If x1 is 0, x2 is 0, then x1 complement is 0, and if both are 1, then again x1 complement is 0. So when you consider this x1 complement as a Boolean formula for two variables, there are two satisfying assignments. So is not a yes instance, nor a no instance. And the last option was x1, x2. Oh yeah, this one. I just can't draw a straight line. Yeah, this is reasonably straight. x1 or x2 and x1 complement or x2 and x1 or x2 complement. So when x1 and x2 both are 0, the OR would be 0. This OR, second OR, would be 1 because x1 complement is 1. And the third OR would also be 1 because x2 complement is 1, but since this is an AND, this would be 0. So when x2 is 1 and x1 is 0, the first clause would be 0, the second clause would be 1 because so when x2 is 1, the first clause would also be 1. The second clause would also be 1 because x1 complement and x2 both are 1. But the last clause would be 0 because x1 is 0 and x2 complement is 0. So again, AND is 0. For 1, 1, the first clause would be 1. Let's try 1, 0 first. So for 1, 0, the first clause would be 1. The first clause would be 1. The second clause would be, so x1 complement is 1, x2 is 0, so this is 0. And the third clause would be 1, so still 0. And for 1, 1, x1 or x2, that is 1. x1 complement is 0 but x2 is 1, so again 1. x1 is 1 and x2 complement is 0, so again 1. So there is exactly one satisfying assignment, so this is a yes instance. Okay, so the answers are A and D. But so we solved D in this way, right? I am claiming there is an easier way to solve D. So would you like to try to guess what that easier way is? So it's the following observation. That this formula x1 or x2 and x1 complement or x2 and x1 or x2 complement, this is the same as the complement of x1 complement or x2 complement. Why? Because there are like 4 max terms, right? these three, and this is the last max term. So if you have an end of 3 max terms, it has to be the complement of the remaining max term, right? So this is
Yes, yes, yes.
x1, sorry, x1. So this is x. Why I'm choosing a laser pointer? So this is x1 and x2, which we saw in option A is a yes instead of u set, right? So this was another easier way of solving this.
Yes.
Yeah.
Yes.
So that's all the problems for today. So if you don't have any questions, we can meet next time.
Yeah.
Yeah.
Thank you.
Thank you. Bye.